Hello, good morning, dear students. Once again, I am here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Department, Bharati College of Engineering and Technology, Durg. Dear friends, last time we have seen Discrete Time Signals and System, Part 3. Now we will go the same Discrete Time Signals and System Part 4. Today we will learn about the causality and stability of the discrete time linear systems. As we have seen, what is the causal condition and what is the stability condition. Today we will go through this stability and causality of the systems. Let us see now stability. What is stability? Stable systems, every bounded input produces a bounded output. Shortly it is abbreviated as BY system. That is bounded input and bounded output. This is called as stable system, you know. We have already seen this one also. And necessary and sufficient condition for the BY stable is given by this S is equal to summation K is equal to minus infinity to infinity. Magnitude of H of K is less than infinity. This is the condition for the stability, necessary and sufficient condition, you can say. Once this condition is verified, the system is said to be a stable system. Here, show that if X is bounded and S is less than infinite, then Y is also bounded, where S is the stability factor. Magnitude of Y of n is equal to summation in magnitude, summation K is equal to minus infinity to infinity, H of K X of n minus K, which should be less than or equal to M, which is finite value. Summation K is equal to minus infinity to infinity, magnitude of H of K less than infinite, where M is maximum of X of n, max of X of n is the function. Show that if S is equal to infinity, then one can find a bounded sequence X such that Y is also bounded. That is the condition for the stability. Let us define X of n is equal to H of minus n, H star of minus n divided by magnitude of H of minus n, where H of n is not equal to 0 and its value is equal to 0 when H of n is equal to 0. This is the regarding stability. Now let us see the causality. And you are already aware what is the causal system. Causal systems are those, causal signals are those in which output depends on the present and the past values. And what is the causal systems? Output for Y of n naught depends only X of n. Depends on only X of n. With n less than or equal to n naught. A causal system whose impulse response H of n satisfied, H of n is equal to 0 for n less than 0. This is the necessary and sufficient condition for the causality of the system. You can see here H of n is equal to 0 for n less than 0. Like the stability, the condition of the causality for a system is this one. H of n is the impulse response is equal to 0 for n less than 0. Let us see this example. Show that the linear shift invariant system with impulse response h of n is equal to a to the power n u of n, where magnitude of a is less than 1, is stable. You have to show that stability S is equal to k is equal to 0 to infinity magnitude of h of k is equal to k is equal to 0 to infinity a to the power k is equal to 1 upon 1 minus a for less than infinity. This is a standard geometric series formula by which we can show. Then discrete time signals and system. Linear constant coefficient difference equation. Nth order difference equation. This is difference equation are very important for digital signal processing also. This difference equation nth order is given by summation k is equal to 0 to n ak y of n minus k is equal to k is equal to 0 to m bk x of n minus k, where ak and bk are the coefficients. Bk are the coefficients related with the input, while ak are the coefficients related with the input. This is called as nth order difference equation in the discrete time domain. Examples: ideal delay system, which is given by y of n is equal to x of n minus nd. Nd is the number of delayed sample. Ndth sample. Moving average is y of n is equal to 1 upon m plus 1 summation k is equal to 0 to k minus m x of n minus k is the moving average sample. Then accumulator, which is given by y of n minus y of n minus 1 is equal to x of n. Such type of any equations which is dependent on the either it is a past or present or in the accumulator. Compute y of n. This is the difference equation given once again. K is equal to 0 to n ak y of n minus k and k is equal to 0 to m bk x of n minus k. Then y of n is equal to minus k is equal to 1 to n ak by a0 y of n minus k plus k is equal to 0 to m bk by a0 x of n minus k. A naught is divided to both the side. Y of n is equal to x of n minus nd. H of n is equal to del of n minus nd. H of n is the impulse response and y of n is the total response of the output. Then you can see here x of n applied to the delay. These are the delay units. You will get the y of n. And number of delays in Z transform is given by Z inverse by one delay. You can connect Z inverse in series by the number of delays. X of n, nd samples delays. You will get the y of n. Nd is the number of delayed samples. Here y of n is equal to 1 upon m plus 1. K is equal to 0 to k minus m. X of m n minus k. And here h of n is equal to 1 upon m plus 1. Summation k is equal to 0 to k minus m del of n minus k. This is the impulse response and y of n is the output response. This impulse response can also be written as 1 upon m plus 1 u of n minus u of n minus m minus 1. You can write in this fashion also for the delayed impulse. And this delayed impulse can also be modified as del of n minus del of n minus m minus 1 star u of n. You can see this one modified equation y of n. This is moving average equation. Y of n is equal to 1 upon m plus 1. Summation k is equal to 0 to k minus m x of n minus k. And h of n is equal to 1 upon m plus 1 del of n minus del of n minus m minus 1 star u of n. And diagrammatically you can see here attenuator 1 upon m plus 1, and this is feedback, forward path m plus 1 sample delay. This is forward path m plus 1 sample delay, and this is accumulator system. So you can form the discrete time system with for a moving average here. Then discrete time signals in frequency domain representation of discrete time signal and systems. Sinusoidal and complex exponential sequences play an important role in DSP, sinusoidal and complex exponential sequences. This is the LTI system having a impulse response h of n, and the complex input is x of n is equal to e to the power j omega n, and you will get the output as a convolution. Y of n is equal to k is equal to minus infinity to infinity h of k x of n minus k. So this is the response with convolution. Now you can convert this in terms of the complex, that is e to the power minus e to the power j into n minus k into omega. You can put in place of this x, e to the power j omega n in place of n minus k. This is modified. You can see here summation k is equal to minus infinity to infinity h of k e to the power minus j omega into e to the power this j n omega, j k omega and j n omega, k omega, and this is j k omega and this is j n omega. Separate it and you will form this bracket shown here becomes a h of e to the power j omega as per the definition, and this becomes e to the power j n omega. So this can be separated and you can get the frequency response. This is the e to the power j omega n is the input. This is the response or transfer function h of e to the power j omega, and this is h of e to the power j omega into e to the power j n omega. You can determine the eigenfunction shown here, eigenvalue and eigenfunction. This is eigenvalue and this is eigenfunction. H of e to the power j omega is equal to summation k is equal to minus infinity to infinity h of k e to the power minus j omega. This is the equation given. This equation can be split into real and imaginary part. HR is the real part and this J is the imaginary part. You can get the magnitude of this and phase angle of this. Magnitude and phase angle. This is called as frequency response. So this frequency response can be obtained. The delay, ideal delay system. This is delay given by y of n and h of n, and this delay can be written in terms of this equation. You can write the delay here and find the magnitude, that is equal to 1 for ideal response, and phase is given by minus omega n d. So this is the system shown here. X of n is equal to a cos omega naught n plus phi, and for which you can calculate its real and imaginary parts, x of n and y of n, as shown in the figure, like this. And this is the response for h of e to the power j omega plus 2 pi. You can separate it and calculate this response like this. This is the frequency response of magnitude of h of e to the power j omega with respect to the omega. This is omega and this is magnitude here. Periodic nature of frequency response you can say from the diagram, and generally we choose omega, range of omega is from minus pi to pi to represent one period in frequency domain, or you may represent from 0 to 2 pi also. This is low frequency response, high frequency response shown in figure here. Ideal frequency response filters. This is the ideal filter shown here. 3 types of filter. Selective filter, pass band, band stop, low pass filter, band stop filter, and high pass filter. These filters can be seen. This is the moving average shown here. You can go through the moving average and calculate the values for different responses. So this is the moving average response, frequency response for M4 filters, low pass, and try larger M. Thank you very much, dear friends. Next time we will go for the representation of sequences by Fourier transform. Thank you very much for listening. If you have any doubt, you can ask me at any platform at any time. Thank you very much.